In this chapter, my goal is to make you an expert in Python functions. Let's warm up with a few examples that get progressively trickier. This mutable default argument gotcha gets repeated so often that most of you probably find it child's play. What about this one? We define 3 functions in a loop, each returning I. What do you think will happen when we call them? Before we look at the output though, let's write this compactly using a lambda, which is just a function without a name in Python. Or even more compactly, using a list comprehension. Do you expect the output to be 1, 2, 3? We get 3 threes instead. Next up, a simple function that prints a global variable. This will output 2026 as expected, no surprises here. Now we make a small change. Inside the function, right after the print statement, we reassign x to 2027. Would this still output 2026 or maybe 2027? Neither. The print line that worked fine before now raises an error. By the end of this chapter, instead of memorizing these examples, you'll be able to understand and explain why they behave the way they do. But let's see a couple of harder ones first. Decorators are a powerful Python feature that lets you change how a function behaves. They're also a common source of confusion. Here we have 2 decorators. What happens when we run this code? Note that we never call f. We're only defining functions, and f itself does nothing. This output goes against our intuition in 2 ways. First, we don't expect function bodies to run without an explicit call. Second, even if we somehow accepted that these 2 prints happened, the order of execution seems to be reversed. What if we also called the function f? Would it print anything again? We get a runtime error. We'll see that decorators aren't magic. They follow a few simple rules, the same ones that govern how functions work in general. Things are getting a little spicier now. What happens if we call this function? Will it print hello and goodbye, or just print hello and stop at the yield? And it prints nothing. But don't worry if you got it wrong. We'll learn all about generators. The final boss of this chapter is going to be a function that calculates a running average. We'll also learn how Python executes functions under the hood, but we have to work our way up to that level. Functions let us wrap up instructions and reuse them with a single call instead of repeating ourselves. They make our code easier to understand, reason about, and test. For example, given the radius of a circle, we can write functions that calculate its circumference and area. Functions can receive input and return output, though they don't need either. But in Python, if a function doesn't explicitly return a value, it returns none. A parameter is the variable listed in the function definition. An argument is the actual value passed in when it's called. That said, people use the 2 interchangeably, and you can tell which is which from context. You'll also see star args and double star quargs in function signatures. Star args gathers any positional arguments into a tuple, and double star quargs gathers any keyword arguments into a dictionary, so a function can accept any number of arguments. They show up most often when a function forwards its arguments to another, like a decorator wrapping the function it decorates. The names are just convention. The star and the double star are what matter. When a more descriptive name fits, use it instead of a generic double star quargs. Functions are first-class citizens in Python, meaning they're objects, like everything else. We'll see they can be passed into and returned from other functions. That gives the language a lot of power and flexibility, but the catch is your mental model of functions has to grow. By the end of this chapter, that bigger model will feel natural, because you'll understand how functions actually work. Writing functions well is important, especially so in the age of AI coding. Here are some practical tips. First off, if you want to blend in with the Python crowd, use snake case when naming your functions and variables. The name should usually start with a verb and tell you what the function does. For example, you can use is, has, or can for functions that return booleans. Be consistent with verbs that are common across programming languages. Implementation details can change, so name a function for what it does, not how it does it. Be specific, but strike a balance. Avoid names that are too generic or too long. Try to avoid abbreviations as they can be confusing. Prefer early returns over nested if-else statements. They keep your logic flat and easy to follow. Functions should do one thing. It's not always clear what one thing means, but if you can't break the function down any further, that's usually a good sign you've captured its single purpose. Whenever possible, a function should either modify an object in place or return a new one, not both. Last but certainly not least, use type hints. At a minimum, annotate your parameters and return values. Type hints make the function's expected inputs and outputs clear, help third-party tools catch bugs earlier, and make code easier to read, refactor, and use correctly. We already covered typing in depth in another chapter. When you define a function, Python creates a function object in memory. Python passes arguments by assignment. When we call get circumference of 5, Python binds the name radius to the integer object 5. Since 5 is a small integer, it's already cached in memory, so Python reuses that cached object instead of creating a new one. If you have experience in other languages, this is neither pure pass-by-reference nor pass-by-value. Python shares the object through a new local name binding, so if you pass a mutable argument, changes you make to it are visible outside the function too. As you develop a library or application, you'll often add functionality to existing functions. For example, we might want to round the output. The problem is we just broke all the existing code that calls getCircumference. A type checker can flag this without even running the code. Since backward, forward, sideways, and all sorts of compatibility matter in programming, the usual fix is to give n digits a default value. Here, n digits defaults to none. When Python executes the def statement, it evaluates that default right then. This is called early binding. None is a singleton, already in memory from the moment Python starts, so n digits just binds to that existing object. With this knowledge, we're ready to graduate from kindergarten. In this code, the cart default is created once when the function is defined at what people call import time. The usual way to sidestep this, while still giving each call a brand new list by default, is to use none as a sentinel. Back to our circle example. We see different kinds of names here. Radius and n digits are parameters, but there's also math.py and round, even though those aren't parameters. The parameters and any name assigned inside the function are its local variables. Here, those are radius, n digits, and circumference. If Python can't find a name in the locals, it looks at the global scope next. In Python, global really means module global, not a universal global across the entire program. Math is a global object. It lives at module level, outside the function, but we access it inside. Finally, round is a built-in, a function Python gives you automatically. Unlike math, it doesn't need an import. To resolve a name like round, Python checks locals first, then globals, then built-ins. Since globals and built-ins don't live in the function's scope, their values can change between defining the function and calling it. Those names are looked up fresh on every call. This is late binding, the opposite of the early binding we saw with default arguments. So we can call getCircumference, reassign math.py to 3, then call it again, and get a different result, even though we changed math.py after defining the function. We can even redefine round entirely, which is called shadowing. This is also what happened with our earlier loop. By the time we called the functions, I had already become 3, so all 3 resolved I to 3. We messed with our globals for learning purposes. Let's revert them as a side quest. Right now round exists in both the globals and the built-ins, so if we delete it from the globals, Python falls back to the built-in. That was easy. Restoring math.py is harder because math is a C extension module. Reloading it doesn't work, but you can pop it from the module cache and import it fresh. All of which is to say, messing with globals and built-ins like this is usually a bad idea. Now we're also ready to understand what's happening here. The moment Python sees an assignment to a name anywhere in a function, it treats that name as local for the whole function, even on lines before the assignment. So inside show year, x is local, but at runtime, the print line errors because x is now local and hasn't been assigned yet. Without the x equals 2027 line, Python wouldn't treat x as local. It would look it up in the global scope and find 2026, exactly like our first version. Congratulations on graduating high school. We mentioned that functions are objects too, like everything else in Python, which makes them first-class citizens. So we can define functions inside other functions, or pass them around as arguments and return them. This turns out to be useful when you want to add the same behavior to many functions. For example, say you want to log every call to your fetch weather and send notification APIs. The naive way is to add a couple of prints. Note that the fetch weather API returned a different temperature the second time we called it. Let's try this further with a log call function that takes an existing function and returns a new one that wraps it. Instead of a couple of print lines, we added many more lines. We can justify this for pedagogical purposes, but in real code bases, you should be really careful about over-engineering. Now, on the right-hand side of fetchWeather equals log call of fetchWeather, we call the already defined log call with our original fetchWeather as the argument. Its body runs, but all it does is create the inner new function. The body of new function doesn't run yet, so we see no print output. The name fetchWeather is then rebound to the new function log call returned. The same story happens with send notification too. The actual call to fetch weather only comes at the end. The log call function we just wrote is actually a decorator, and Python gives it special syntax, the @ symbol, to save you from writing function equals decorator of function each time. The @ syntax hides everything we just walked through. But now that you've seen it once, you know the @ symbol before a function is just syntactic sugar, nothing more. What if we also wanted our logger to track some statistics, like how often each argument value shows up, and log that too? That's easy with some containers. Here, two good choices are default dict and counter from the collections module. We place them inside log call, but outside new function, so they persist separately for each decorated function. Now we can track some calling stats, and we only needed to modify our decorator without touching any decorated functions. Earlier, we said functions resolve names through locals, globals, and built-ins. So what is counter dict to new function? It's not local, since it's not created inside new function, and it's not global or built-in either. It lives in a fourth scope I held off on until now, which is called enclosing, the scope of an outer function that wraps an inner one. So when Python resolves a name inside a function, it follows the LEGB rule. Local, inside the function. Enclosing, in a surrounding function if any. Global, module-level names, and built-ins, built-in Python names. One side note, because our wrapper only accepts keyword arguments, calling fetchWeather with the capital city of Turkey and Celsius positionally without the city and units keywords raises an error. To signal that our API only accepts keyword arguments, we use a star, like this. The slash does the opposite, forcing the arguments before it to be positional only. Anything between a slash and a star can be passed either way, and this works for any function, plain or decorated. For example, here greeting is positional only, excited must be keyword, and name can go either way. These slash and star markers have more use cases, or they wouldn't be in the language. Python's core developers are careful about adding new features. This is unlike AI agents' vibe coding features nobody asked for. Because our decorator replaces the original function, we lose some of its metadata, including its docstring, name, and type annotations. To fix that, you can apply functools.wraps, which copies those attributes from the original onto the wrapper. Without it, help shows the wrapper instead of your original function. When you apply functools.wraps, you get the original name and docstring as expected. Decorators can also take arguments. That means another layer in the funception, a function that spits out the decorator based on its arguments. For example, a file-like argument that says where to log, pass straight through to print. Now log call takes an argument and returns the decorator, so there are 3 layers instead of 2. If you get confused about how this works, you can always lose the syntactic sugar. You've been using decorators like these all along, from libraries like FastAPI and Tenacity. But if your decorator is turning into a monster like this, it's often cleaner to write it as a class instead of a function. We'll see how in a future chapter. Finally, you can stack multiple decorators. Just remember they compose like math functions applied from the inside out. With that rule, we can follow what's going on in this example. First, notice our decorators never do anything with the arguments they receive, which is why we name the parameter underscore, signaling that we don't use it. Remember, without the @ symbol syntactic sugar, it's equivalent to this. Initially, second of f runs, so it is actually called. The @ syntax is hiding the function call. After second runs and prints, it implicitly returns none. It never even defines an inner function like a normal decorator would. Then first receives that none, and just like second, ignores it, prints first, and returns none. So f isn't a function anymore, it's just bound to none. That's why calling f raises a type error. Pat yourself on the back, this was your college graduation. Sometimes it's cooler not to be a college dropout. When a big first mover company tells you it's hopeless to compete with them, how would you reason about that decision? Game theory helps us model strategic interaction. Here, we can use an extensive form game between 2 players, an entrant and an incumbent. The entrant moves first and decides whether to enter the market. If it stays out, the incumbent keeps its monopoly. So, the entrant gets 0 and the incumbent gets 4. Every leaf of the tree shows a payoff for both players. Payoffs have no cardinal meaning. We only care which one is larger, that is, their order. If the entrant enters, the incumbent decides how to respond. Either fight a price war, which makes them both lose money, or accommodate and share the market half and half. The question then is, standing at the top of this tree, how do we figure out what each player will actually do? The answer we're looking for is called a subgame perfect Nash equilibrium. It is a set of choices where, in every subtree or subgame, no player can do better by changing their move, hence the name. We can find it using a simple algorithm called backward induction. Start at the bottom of the tree, and at each decision, let the player take the branch with the best payoff for them. Then carry that result up to the node above. In our example, this means that if the entrant enters, the incumbent should accommodate, because 2 is larger than -1. Knowing that the incumbent would accommodate, it's then better for the entrant to enter than to stay out, since 2 is larger than 0. But how do we implement backward induction in code? The value of a node depends on the values of the nodes beneath it, which depend on the ones beneath them, and so on. A function that solves a node by solving its children is a function that calls itself. This is known as a recursive function. The solution dives to the bottom of each branch before comparing, then carries the best result back up. This traversal is a depth-first search. Recursion is powerful, but there's no free lunch. Take the Fibonacci sequence, where each number is the sum of the two before it. Our recursive implementation is elegant but extremely slow. We can see why if we count how many nested calls happen inside a single call. How can we do that? Should we print at the start of the function? Or instead, we could just reuse the log call decorator we wrote earlier. Back then, our decorator only took keyword arguments. Fib calls itself positionally, so let's generalize our decorator to accept *args too, and count each value as it comes in. The same values recomputed over and over, a whopping 2.7 million calls just to get fib of 30. We can fix that with the cache. Store each result the first time, then reuse it instead of recomputing the same value. Again, for teaching purposes, we can use a decorator to modify the behavior of a function. Our log call decorator now lives in its own file, so we import it. Now every value is computed exactly once. We get 31 calls instead of millions. And notice we just stacked 2 decorators, the same composition we saw earlier. I encourage you to also implement and time both versions. You'll see that the function is now tens of thousands of times faster from one extra decorator. In your code, you don't need to write the caching behavior from scratch, like we did here. The standard library has functools.cache, which does what we built. There's also functools.lrucache, which is the same idea, but bounded, keeping only the most recently used results, so it can't grow without limit. The cache removes the repeated work, but Recursion has another catch. It can go too deep and the stack overflows. Python lets you raise that ceiling. Even then, you can still crash the interpreter. Recursion is elegant, often the most natural way to describe a problem, and genuinely satisfying to write. But in production, the safer move is usually to flatten it, because anything you can express with recursion you can also write as a loop. Here's a clean non-recursive Fibonacci function. It needs no caching and no recursion limits to worry about either. Python has a built-in range function, mostly used as a helper for iteration. It's special because its memory footprint stays tiny, no matter how large the range. You can give it enormous bounds, and it doesn't load all those numbers into memory. Instead, it gives them back one at a time. How can a function pause its execution and hand control back like that? Normally, a function call is eager in the sense that it runs from start to finish in one go. The yield statement lets a function pause that execution, and if it's followed by a value, it will hand that value back to the caller before pausing. This works like range, except the built-in range makes start optional and accepts more than just integers. One more bit of trivia. Range isn't even a function, it's an immutable sequence type. But that's what duck typing is about. Range looks and behaves like a function, so everyone calls it one, the official Python docs included. If you look at the type of my range we created, it's a function. Once you call it, you get a generator type. A generator object is an iterator. Python can ask it for values one at a time with the next function. You'll sometimes see its type written as iterator of int rather than generator of int, none. When Python reaches the yield start line, it returns the current value of start to the caller, but it doesn't destroy the function's local state. Its local variables, instruction pointer, and execution context are kept alive inside the generator object. This is why generators are lazy and memory efficient. They don't compute every value ahead of time. They only compute the next value on demand. The for loop hides this machinery from us. It's roughly equivalent to this. When it finishes, Python raises stop iteration behind the scenes to signal that there are no more values left, which the for loop handles gracefully. A lesser-known fact about generators is that they aren't a one-way street. You can also send a value back into 1, where it becomes the result of the yield expression inside. Let's use that to let the caller rewind our range. Each generator has 3 type parameters: the yield type, the send type, and the return type. Our first version only yielded integers and never received or returned anything, so it was generator of int, none, none. This one still yields integers, but now it also receives 1 through send, or none when you use plain next, so the send type is int or none. So yield start now does 2 things at once. It hands start out, and whatever the caller sends back lands in step back. With next, nothing is sent, step back is none, and the range marches forward as before. But send a number, and the range steps back by that much first. The first call has to be next, or send with none, because there's no paused yield to receive a value until the generator has started. That first step is called priming the generator. There's still the third type parameter we haven't used. A generator can also return a value when it finishes, separate from what it yields. I've never needed this in production, but I'm including it for completeness. Let me know if you've ever had a legitimate need for it in your code. We'll have my range count how many values it handed out. That return value is never yielded, so a for loop or next won't give it to you. It's packed inside the stop iteration that ends the generator. One clean way to read it is yield from, which re-yields every value from another generator and then evaluates to whatever it returned. And that's your master's degree, because now you can easily reason through why nothing is printed here. We never advanced the generator we got from calling my function. But if we did, the first next runs up to the yield and prints hello. The second resumes, prints goodbye, falls off the end, and raises stop iteration. This was a long introduction, but you are now ready to see what's behind the curtain and get your PhD. In this channel, we bridge the gap between writing Python and shipping production-ready Python, covering the essential ideas and tools you need to get there. So far in this chapter, a function has been a practical tool, a way to organize code and build abstractions. But there's a deeper answer to what a function is, one that goes back to the definition of computation itself. In the 1930s, 2 people tried to answer the same question. What does it actually mean to compute something? We all have an intuitive sense of algorithms and computation, but can we make it rigorous? Alan Turing's answer was his Turing machine, a device with modifiable state on a tape and a list of instructions that can read and rewrite it. That's the same idea at the heart of the von Neumann architecture, the CPU and memory design inside the device you're using right now. Alonzo Church's answer seemed completely different. His lambda calculus had no mutable state, just variables, function definition, and application. Except the 2 approaches turned out to be equivalent. Anything you can compute with one model, you can compute with the other, and vice versa. That equivalence backs what's called the Church-Turing thesis, the claim that these models capture what it means to be computable at all. An interesting fact is that Alonzo Church was Alan Turing's PhD advisor. Even though they built their theories independently, perhaps they shared some common inspiration. In hardware and most programming languages, though, Turing's theory won. Every mainstream computer is a state and instructions machine, not a function reduction one. Most programming languages are modeled after mutable state and instructions, but Church's lambda calculus became the center of functional programming. If you go even deeper, at the root of lambda calculus is combinatory logic, a system that has no bound or quantified variables at all. Someone named Curry worked on combinatory logic extensively. You may have heard of him by his first name. Haskell Curry's PhD advisor was the David Hilbert. Hilbert posed a million questions that kept all the big brains occupied for more than 100 years and counting. But one of the problems he asked was the decision problem, which is what Church and Turing answered independently in 1936. Kurt Gödel had already shown in 1931 that there are true statements in mathematics that cannot be proven, and Church and Turing showed that there are problems that cannot be solved by computation. This was a big blow to Hilbert's quest to know everything, but that's for another time. All this history has a lot of loops and rabbit holes of its own, but one of the things Haskell Curry discovered was the Y combinator, which lets pure functions recurse without a name. That's where the startup accelerator Y Combinator got its name, a company that produces other companies recursively. Where does Python sit? Python is, first and foremost, an object-oriented language. I think at this point you've heard a dozen times that everything in Python is an object, and also that Python has mutable state and instructions. The CPython interpreter is a virtual CPU executing compiled bytecode. Yet, Python borrows a handful of tools from functional programming. We've already seen 2 of them, lambdas and closures. There are also partial to freeze some arguments, map, filter, and reduce to transform, select, and collapse a sequence, and single dispatch to run different code depending on a value's type. None of these make Python a functional language, though. They're useful functional ideas, borrowed into an object-oriented one. In the last chapter, we learned that Python compiles code to bytecode, and the CPython virtual machine runs it one instruction at a time. Functions add the code object and the frame on top of that. When Python reads a def, it compiles the function body into a code object, which is an immutable bundle of bytecode and constants. The code object of a function is built once and shared by every call. Make function wraps that code object into the function you can name and pass around, and call is what runs it. This already explains the first gotcha of the chapter. The build list runs once, at definition time, and the list it makes is attached to the function as its default. Every call that omits cart reuses that one list. A quick word on the stack data type. A stack is a simple structure. You only add to or grab from the top. This is also known as a LIFO, last in, first out. I'd like to think this is similar to how I handle 100 open tabs in my browser when I'm researching something. I jump from one topic to another, then return through them one at a time as I finish each. Stacks are widely used in computers. Your CPU keeps a call stack too. Calling a function pushes a return address onto it and returning pops it back off. There's also stack memory, fast to allocate and organize the same way, as opposed to the heap. Python's virtual execution model mirrors the hardware. During function definition, you can see decorators being called. Because of the last in first out order of the evaluation stack, the innermost decorator is called first, then the next one, and so on. Each call to a Python function creates a frame of its own. It has three conceptual sections. First, it has local variables. Second, it has its own evaluation stack, where values are pushed and popped as the bytecode runs. And third, it has specials, the bookkeeping the Python interpreter needs to run the frame. This includes the code object, globals dictionary, stack depth, previous frame, instruction pointer, and so on. Locals in the frame are reached with load fast. Fast, because they're slots looked up by position, not by name. When showYear only reads x, the compiler loads it as a global. When x equals 2027 is in the function body, the load becomes load fast check. This checks if the local slot is filled. At the print line, it isn't yet, which gave us the unbound local error we saw. The 3-3's closure gotcha happens because the free variable I is looked up only when the function is called via load deref. There are two different stacks in play when Python executes your functions. Each frame has its own evaluation stack for operands. The thread has a single call stack, a stack of frames, one per active call. When my func runs 42 plus my other func, it pushes 42 onto its eval stack, then calls my other func. At the call, Python pushes a new frame for my other func onto the call stack. My func is now suspended, still holding 42 on its own eval stack. When my other func returns, Python pops its frame, follows the link back to my func, drops the result onto my func's eval stack, and the addition finishes. Python keeps these frames in one contiguous per-thread block, tracked by a frame pointer and a stack pointer. This is also why recursion has a limit. Every call pushes a frame, and a recursive function calls itself, so each level adds another frame to the call stack. A generator's frame works the same way, but it isn't allocated in the per-thread call stack. It's embedded in the generator object itself, which is what lets it outlive a single call. Calling a generator function doesn't even run the body. The first opcode, return generator, hands you the generator object and returns, which is why calling my function back at the start printed nothing. The body only runs once you advance it, and each yield compiles to yield value. It drops a value back to the caller, just like return value, but instead of discarding the frame, it remembers where it paused, so calling next or send again resumes right after the yield. We're now at the final boss, a function that computes a running average. We want it to take an integer and return the average of every integer it has seen so far. This can be implemented in many ways, and we'll improve our solution step by step, using everything we learned in this chapter. The obvious first try is to collect the numbers in a list and average them. This works, but values grow forever, consuming more and more memory and slowing the function down as the list gets larger. Since we don't need the individual numbers, only their average, a running total, and a count can give the same answer in constant memory. In order to reassign a global variable from inside a function without an unbound local error, we have to declare it as global. The state is now two globals, and globals are undesirable for many reasons. For example, anything in your program can overwrite total or count. You can only run one average at a time, and globals make the function harder to test. We can instead tuck the state inside a function that returns another function. Now the state is private to each averager function, The non-local keyword is what lets the inner function reassign the enclosing total and count. It's the closure equivalent of the global keyword. Again, without it, we're back to an unbound local error. So far, so good. What if we only want the average of the last n numbers, a moving average? We need a sliding window, and the right tool is a dec, pronounced dec. A double-ended queue appends and pops from either end in constant time, and once it's full, it drops the oldest item automatically. With a window of 2, the third value pushes out the first, so the last average is over 20 and 30, which is 25. We could also keep a running total like before and subtract the oldest value when the window is full, but fmean is fast enough for this example, and the dec keeps memory usage fixed. Can we avoid nested functions while keeping the state private? Let's try it with a generator and send. You could also hide that priming call behind a decorator, but I'll leave that as an exercise for you. An implementation like this shows that you have a solid understanding of Python functions, data types, and control flow. The real wisdom is knowing that this is too much complexity for a simple running average. We have yet to cover Python classes, but they can do the same job with far less ceremony. Or, if you already import third-party data libraries, one of them probably provides an optimized, battle-tested moving average. And that is your PhD in Python functions. In this chapter, we covered a lot about functions. Except there's one kind of function we left out on purpose, async def. This pulls us into different waters: concurrency, parallelism, and the infamous GIL. That's our next chapter. See you there.